Hey class, so we have to talk about our intro to day 5 of notes, which is day 2 of this section, but this is day 5 of our notes for this class, and we're still talking about radicals, but there is a lot to uncover here, so we want an intro to make things easier for us the next time I see you. So the first thing to keep in mind for adding and subtracting radical expressions is to simplify initially. Okay, you want to start by simplifying each radical individually, and then you can only combine if you have like terms, which in this case I'm going to call like radicals. So they have to have the same exact index and the exact same insides, okay? So for example, if I had square root, let's say I had 3 root 2 plus 5 root 2, that's like having a 3x plus 5x. 3x plus 5x is 8x. This would just be 8 root 2. That root 2 is like an x. It cannot be simplified. The square root of 2 is not a nice number, but I can combine it with anything else that has a root 2. If I had 3 root 2 plus 5 root 3, that could not be combined. Why? These are not the same insides. This would be a trick question. The answer to this question is literally just this, okay? It's like having a 3x plus a 5y. You just leave it. So let's do our examples. Now, obviously it looks like these, the first one I'm doing is this highlighted one. It looks like these 3 would not be able to be combined because they all have different insides. However, that is why I have to simplify first, because it looks like they're not like terms, but after simplifying, they might be. So these are square roots, so let's find some perfect squares. 18 is 9 times 2. Oops. And this k, obviously, is not going to be reduced because there's not enough k's inside of the radical. So let's square root everything. The square root of 9 is 3, and the 2k cannot be reduced, that stays inside. But don't forget I had this 4 in front, so right here I have 12 root 2k. And I'm going to keep doing that. 72 is 36 times 2. Again, that k is going to be left over on the inside. Square root and square root. So this is going to be, there's nothing to multiply by, so it's going to be square root of 36 is 6, and then square root of 2k. And I just dropped that minus down. That's where that came from. So notice I do have like terms there. And last one, 50 is 25 times 2. Square root of 25 is 5. Square root of 2 does not work. The k is still inside. Notice I now have all like terms. So I can combine. 12 minus 6 is 6, plus 5 is 11. Final answer is 11 root 2k. So we simplify first and then combine like terms if possible. Same is true with cube roots or fifth roots or whatever. Any index, it's the same strategy. So next I'm going to do this one right here. Now this cannot reduce. Why? Because no number that goes into 4 is cube rootable, and there's not enough x's, so I'm just going to leave this be. Now, one hint is that since this inside is 4x, I bet the other insides will also be 4x. So if I think about it, let's see, 32 divided by 4 is 8, and hey, turns out 8 is a perfect cube. The cube root of 8 is 2. Don't forget this 5 here. So cube root of 8 is 2. And I still have the cube root of 4, and this x stays in. Cannot be reduced. So that's going to be minus 10 cube root 4x. And I still have this original cube root 4x. I'm just going to pull that down. Last one, 108. Let's see, divide that by 4 and it's 27, and hey, that's a perfect cube. So the cube root of 27 is 3. Don't forget that 2 there. 2 times 3 is going to give me a plus 6 cube root of 4x. And sure enough, I have all like terms. Let's combine. There is an invisible 1 coefficient with the first one. 1 minus 10 is negative 9, plus 6 is negative 3, times the cube root of 4x. Beautiful. All right, guys, moving on. So the rest of this page we're going to do together in class because things get a little complicated. We are going to move on to some other quicker examples. The next topic we're going to be talking about is rationalizing. So rationalizing happens when there's fractions. Sometimes fractions are easier when they can be simplified without needing to rationalize. So one thing I wanted to remind you of from Algebra 1 is that if I have a big radical like this, I am able to split it up into the top and into the bottom. So the square root of 25 is 5, and the square root of x squared is x. Square root of 81 is 9, and hey, this came out pretty nice. And the same is true for the next ones. You can do the same thing. It is a property of roots or radicals that you can break them up if I have a fraction. So this one is negative. I always put the negative on top. It's just like a habit. So negative cube root of 3 over the cube root of 8. And then the top cannot be simplified. I'm just going to leave it. But the cube root of 8 is 2. Okay, and finally, same thing here. 5th root of s over the 5th root of t to the 5th. Okay, well, on the denominator, the 5th root of t to the 5th is just t. And on the top, I have the 5th root of s. It is okay to leave it if there's no radicals in the bottom. That's all good. If there are radicals in the bottom, we have to do something called rationalize the denominator. Now, rationalizing with higher indexes is a whoops, there's the bell, is a thing, okay? You guys need to learn how to do that. It's not as cut and dry, but you guys have done it before with radicals, like just square roots. So I'm going to remind you how you did that in Algebra 1. To get rid of this square root of 3, we would multiply the bottom and the top by the square root of 3. So on the top, 4 times root 3 is just 4 root 3. On the bottom, I have this original 3. Let's talk about this. Root 3 times root 3 is technically root 9. But what is root 9? Square root of 9 is 3. So I actually am left with that 3 there. Final answer is going to be 4 root 3 over 9. So that is the process of rationalizing with square roots. Rationalizing with higher indexes like cube roots or fourth roots is a little bit more of a process that we will talk about together in class. All right, now I know this video is getting long, so the very last thing I want to talk about is rationalizing if I have a binomial. This is new, but I think you guys will catch on fast, which is why I'm going to do one example. If I have a binomial, it is not so cut and dry of just multiply by the radical. The reason for that is because I would have to distribute and then I would be left over with a radical on the bottom still. So, strategy for this is to multiply by something called the conjugate. And I will teach this more in class. The conjugate is this exact same as the bottom, except switch the minus to a plus. And then, okay, here's a blast from the past. Then we FOIL. Legit FOIL. 5 times 5 is 25. Plus 5 root 3. Here's the beauty of it. Minus 5 root 3. All right, minus root 3 times root 3 is root 9. Root 9 is 3. So when you multiply root 3 times root 3, the root just cancels. This is all in the denominator, and the beauty of all of this is those cancel, and I get 25 minus 3 in my denominator, which is 22. Guys, my denominator no longer has a radical, and life is good. Now I can distribute this root 2. Final answer is 5 root 2. Root 2 times root 3 is root 6. Plus root 6 all over 22. All right. That was fast. I understand. But I wanted to give you guys a little taste of what's coming at you in the next lesson. And there's a lot of examples, so it feels good to get some of them out of the way. If you still have questions, don't worry. Bring them to the Zoom when I see you next. Peace.